Good. So we have seen the torsion map. Which was swallowing two vectors. And was giving back another vector. What does it mean? That is a torsion map is swallowing two vectors and is giving us something that has an index up because it is a vector. Therefore, we have the index C because that's the output of our vector, so of our guys, which is our vector of output. And then we have the two lower indices because it's swallowing two vectors. So it is going to be applied to our vector B, and it is going to be applied to our vector B. So you see, AB, AB, we have a free index which is up. Okay? Now, what we can notice is that if we get our torsion map and we apply to EV and BU, where A and B are two real numbers, then we get AB and T VU. Sorry, this is tight. Okay? That's because what we have here, we have combination of derivatives, and when you have a vector applied to a constant number, a derivative applied to a constant number, it can come out. Okay? That's an inheritance of that. So this tells us that this object is linear, so it has a linear property with respect of multiplication with respect to its ingredients. Okay? Of what it swallows, which is V and A. Since this guy is a vector, we understand that we can define something. If we let it swallow a one form, we get a real number, right? If we have this construction, then I can have a one form and apply to that, then you see that I have something that contains four objects that are swallowed, and it has a tensorial form because it transforms as a tensor, as it can be shown, and because of this property. Okay? So now this new object that we call T is the tensor associated to torsion. So it's the torsion tensor. Torsion tensor that we label as T, that is swallowing a one form, MPT star, so that's something that is living in the space of one forms, in the dual space of the tangent space PT, MPT. It swallows two vectors and gives you a scalar. We can then ask ourselves what are the components of the torsion, and to get the coefficients we just have to let it swallow the basis. We're talking about coefficients, therefore we are defining a frame in which you can have the basis set for frame as we've seen, and we are going to get the coefficient of the torsion tensor. Okay? Just recall the definition of torsion, which is this guy, so the torsion map, which is this guy. U V is equal, sorry, I used VU before, so VU is going to be V U A B. Then we have that's applied to the commutation of the A, the B minus the B and the A. So what we do, we have this object, we are attaching our one form, and then we are going to plug the basis into here to get the coefficients. So let's do that. So the components, right? Which are obtained. So torsion. Now it's let's use the same. Doesn't matter. A, B, and C are going to what? The basis of the one form. So as we've seen, we had a convenient basis, which was our dx A, applied to our torsion map, basis of our vector space, which are derivatives as we have seen, B, and then the basis, B and C, yeah. Like that. Let me change it with that, sorry, C, A, B, C, A, B. So what we do? We just apply our construction of torsion. Okay? We could go through that, but it's more convenient to define our torsion tensor, T. Remember, we had the commutation between two vectors, V and U. Then we had a term which was given by our V A U B, derivative A, derivative B, minus yes, VA. So it was, sorry, it was V A D A U B minus U A D A U B. Right? And the basis dp. Minus the torsion map, which was applied to the V U, and we had the basis B, therefore we had the coefficient B. Okay, remember that the output of torsion is a vector, therefore it has the index up. Therefore, how do we define it? We define it with this guy equal to, we just have to bring torsion on this side and the commutator on the other side. Such that we have a definition for torsion. For the torsion tensor as T U V. Sorry, we had this construction of torsion that gives you our T torsion map B V U, the B equal to, there is a minus, so we bring it here, V. Now look, V alpha, the alpha, this is the directional derivative with respect to A, applied to U, and then we have the directional derivative with respect to U, applied to V, minus the commutator of vectors. That's our definition. That's how we constructed all this object when we started from the commutation of vectors. Now we go for the coefficients, and what we need to do is to apply this stuff to this object. So we are going to basically substitute all of these things with the basis, well, here as well, and apply this object to a one form, like that. Again, the basis of the one form, because we are interested in the coefficients. So, what we get is our dxc, and all of this is multiplied by that using these coefficients, okay? So we are going to have the basis of the vector, coefficient A, therefore d coefficient, So that's the coefficient A, basis C. So this is going to be, sorry guys. Okay, sorry guys. We can stop here for today, and we can continue next time. Okay, sorry for that, but really. Yeah, we can continue next time. Okay, no worries. I will drink, I will recover, and I will be more in shape next time. Okay, sorry for that, really. And yeah, so we are going, so recap of today. So 5 minutes are good for the recap. We went through the manifold, we went to the covariant derivatives. Key concepts are the fact that the covariant derivatives are not unique, but they obey a very specific set of rules. These 4 rules that you have seen, plus